harnessing big data and smart traffic systems to reduce urban emissions. Did you know that urban road traffic is a significant contributor to global carbon emissions? In fact, it accounts for a staggering 11.9% of total greenhouse gas emissions, which translates to around 5.88 billion tons each year. Major cities like London and Paris are particularly affected, with congestion alone generating millions of tons of CO2 annually. To put this into perspective, London's traffic emissions would require a forest the size of Sydney, about 12,000 square kilometers, to offset. But it's not just Europe facing this challenge. In Asia, particularly in China, the situation is becoming increasingly dire. The rapid urbanization in Chinese megacities has seen transport emissions skyrocket from 96 million tons in 1990 to a whopping 996 million tons in 2021. This alarming trend poses a serious threat to China's ambitious goal of achieving carbon neutrality by 2060. So, what can be done? One promising solution lies in adaptive traffic signals. These smart systems can significantly improve urban traffic efficiency by utilizing real-time data to optimize traffic flow. In pilot cities across China, these adaptive signals have been shown to reduce trip delays by up to 15%. Imagine the impact if we could implement these systems citywide. Simulations suggest that adaptive traffic signals could cut vehicle trip times by 8 to 11% and reduce CO2 emissions by over 31 million tons across China's 100 most congested cities. The need for effective solutions is urgent. Urban congestion not only contributes to greenhouse gas emissions, but also hampers progress towards the United Nations Sustainable Development Goals. By reducing congestion in cities like Suzhou, Chengdu, and Harbin, we could potentially lower GHG emissions by 12.7%, 14.2%, and 12.9%, respectively. The key to achieving this lies in harnessing advancements in data collection and processing to develop more effective adaptive traffic signals. Over the years, various strategies have been employed to tackle urban congestion, from traffic restrictions to congestion pricing. While these avoid strategies aim to encourage sustainable travel options, they often require significant investment and time. On the other hand, improved strategies focus on enhancing the efficiency of existing infrastructure. Adaptive traffic signals are a prime example of this approach, dynamically adjusting to real-time traffic conditions to alleviate congestion without the need for expanding road capacity. The technology behind adaptive traffic signals has evolved significantly, moving from heuristic methods to sophisticated machine learning algorithms. Unlike conventional traffic signals that rely on historical averages, adaptive signals can adjust their timing based on current traffic conditions, ensuring that green lights are allocated where they are most needed. However, the implementation of these systems is not without challenges. While multi-source traffic data is available, collecting and processing it can be costly and unreliable. Therefore, there is a pressing need for robust signal timing updates that can function effectively even with limited data. Excitingly, simpler cycle-based algorithms, like Webster's method, have already shown promise in Chinese cities, with pilot projects in Hangzhou and Nanchang successfully reducing trip delays by 15%. This demonstrates the potential of data-driven adaptive control systems to alleviate long-standing traffic issues without exacerbating congestion. Recent studies have taken this a step further by modeling the citywide impacts of big data-driven adaptive traffic signals. Researchers simulated traffic conditions in China's 100 most congested cities, revealing that the benefits of integrating adaptive traffic signals far outweigh the costs. In fact, these systems could reduce vehicle trip times by 11% during peak hours and 8% during off-peak times, leading to an estimated reduction of 31.73 million tons of CO2 emissions. From an economic standpoint, the annual implementation cost of these systems is around $1.48 billion, but the societal benefits, ranging from carbon reduction to improved fuel efficiency and reduced travel times, amount to a staggering $31.82 billion. This clearly shows that the advantages of adopting adaptive traffic signals far exceed the initial investment. As cities continue to grapple with traffic congestion and emissions, the integration of advanced traffic management systems powered by big data could be a game changer. City planners can leverage this framework to assess the environmental and societal benefits of adaptive traffic signals, paving the way for policy shifts that align with transport emission goals and sustainability targets. The future of urban mobility could very well depend on how effectively we harness the power of data to create smarter, greener cities.